Okay, this playlist is going to be about thermocalculus, one of the most difficult subjects I have had to solve problems in or teach in chemical engineering. What's so hard about it? I'm going to start by describing what we're trying to do and perhaps describing a little bit about why it's confusing, and then I'll try to establish the mathematical and thermodynamic basis for this kind of analysis. So the challenge, as I see it, is this. We've got several thermodynamic variables, for example, internal energy, enthalpy, Gibbs energy, Helmholtz energy, and temperature, pressure, volume, entropy. I forgot entropy. That should probably have gone here. And not all of them are measurable. And in fact, sometimes you want to predict, even if you can measure it, you want to predict what a process will do to it. And so these variables are related to each other in complex ways. And depending on the situation, you may want to express any one of these as functions of the others, but there are limitations on how you can do that. Let's just look at a few different examples just to illustrate what we're trying to do. I'm not going to solve them right now. So if I had a process in which a gas at a certain temperature and pressure went through the process and came out the other side at a different temperature and pressure, we may want to know delta H, right? So we may want to know delta H, and perhaps we would like to express H as a function of temperature and pressure so that we can plug in the input and the output temperatures and pressures. H is going to depend on a lot of things, including temperature and pressure, so how do we do that? Alternatively, we may have something going through a Joule-Thomson valve. So with Joule-Thomson, usually you have no heat transfer, no work. That means that delta H is 0. And we have a T out and a P out. They're not necessarily the same as in the other example. Maybe I'll draw a line. This is meant to be a different example. And when you do the analysis, you find out that delta H is 0. So what if you wanted a change in entropy, right? Say you wanted S as a function of T and P, and you also want to say something about the path, right? So what if you wanted ds dt at constant H or ds dp at constant H, so that you can calculate how things vary along a constant enthalpy path. So that's the sort of thing we may want to calculate. How do we do that? I think an important sort of foundational principle here is the Gibbs phase rule, because that puts some limits on how many variables we need to specify. Usually when you solve problems like this, or at least when you're first taught to solve problems like this, you're solving single component, single phase problems. In fact, my examples are going to kind of stick to that, at least in this playlist and in the Thermo 1 course I teach. So Gibbs says the number of degrees of freedom, which means the number of variables you have to independently specify to specify the state of a system, is 2 minus pi plus n, and pi is the number of phases. So I'm going to set that to 1, single phase. N is the number of components. We're not talking about mixtures, right, in the playlist. So that's going to be 1 as well. And so that means that most of the time, I think in all the examples in this playlist, the number of degrees of freedom is going to be 2. So that means that notice that I kind of hinted at that. If we're interested in H and we specify T and P, likewise, if we are interested in S and we specify T and P, that actually specifies the state of the system, and therefore it ought to be possible to evaluate whatever we want to evaluate. Likewise, we could say V is a function of T and P, U is a function of T and S, H is a function of T and V, G is a function of T and P. The pattern here is really that any of these variables can be expressed as functions of any two of the other variables. And because they're independent from each other, if you specify two of them, you specify the state of the system. Notice also that a lot of these variables can't be directly measured. So G, S, or U, S, H, G, A, those are things that you don't really measure directly in experimental data. So one way of, or one other question, like one way of kind of describing what we're trying to do here is we want relationships between things that we can't measure and things that we can measure. Maybe not every problem fits into that description, but often we do. So it's important to ask, what can we measure? So I'm going to talk a little bit about experimental data. So you may not have noticed this, but equations of state, like the ideal gas law, these are usually derived from experimental data. In high school chemistry, I remember my teacher telling me about things like Dalton's law, early experiments done on gases that eventually led people to the ideal gas law. It's not a perfect representation, but it is a representation of experimental behavior of how P, V, and T are related for a gas. Here's another example. This is not an equation of state, but it plays a similar purpose, right? So for liquids, we define things like beta, which is the volume expansivity, which is 1 over the molar volume dV dt at constant P. And we have kappa, which is the isothermal compressibility, and that is equal to minus 1 over V dV dP at constant T. So we treat kappa and beta as roughly constant. In fact, they are close to zero. They're small quantities, and that is meant to reflect the fact that liquids are close to being incompressible. So variations in temperature or pressure tend to have little proportional changes to the molar volume for a liquid. So what else represents experimental data? There's heat capacities. Now, heat capacities refer to how much energy corresponds to a certain change in temperature. Remember, temperature is something you can measure, but it is not an exact measurement of energy. It's more like the currency with which different objects exchange energy. So CV, constant volume heat capacity, is du dt at constant V, and CP is dH dt at constant P. So every substance is different, and the amount of energy you have to put into different substances to change their temperature is different. But I will comment that heat capacities have to be positive. In other words, if you add heat, it has to increase the temperature. But the question is how much. For different compounds, you're going to have different amounts of temperature change for a given amount of energy input. But temperature does always go up with energy. Okay, so let's talk a little bit in more mathematical or abstract mathematical terms. So I'm just going to say math tricks. Some of this is a bit unorthodox compared to what you might have learned in calculus. I'll explain. So if I, for example, have h as a function of t and p, then in Thermo we like to write something called a total derivative. And that means that dh, a differential change in h, is dh dt at constant p times dt plus dh dp at constant t dp. Now, the reason I call this unorthodox is that, at least when I learned calculus, you don't actually write differentials by themselves. At least I never did that in a math club course. You always write derivatives as ratios of differentials. Of course, you could write an integral that involves a differential, but that's a different thing. And the idea is a derivative is a change, a rate of change in one thing in response to a change in another thing. But what this is actually a very common way of writing things in Thermo. What it's meant to imply is that if I have some change in temperature or pressure, that the differential change in H is proportional to the differential change in T and P according to the partial derivatives as constants of proportionality. You can also use total derivative equations to generate other differential equations. For example, if I wanted to know, say, dH ds at constant t, what I can do is divide the total derivative by ds and hold t constant. So this would be, at constant t, dt would be 0, so that term wouldn't be there, and this would be dh dp at constant t times dp ds at constant t. Whoops, that would be a plus. I don't know why you would want to do that, but you can use total derivatives. Or I don't know why you would do this particular one because we're not working on a problem, but you can use total derivatives to generate other derivatives. Okay, partial derivatives, just to be clear, imply that, say, for example, this one, we acknowledge that H depends both on pressure and temperature, so when we take a derivative with respect to temperature, we hold P constant, or we treat it as if it's a constant. And now one thing to be careful of is that the variable being held constant matters. So, for example, dp dt at constant s, or actually v in my notes, is not the same as dp dt at constant s. Even though they might look like they're the same differential, because we're holding different things constant, they are not the same. Now, one thing you can do is flip a differential. So you can, I'll say, derivatives can be flipped. So, for example, ds dt at constant p is 1 over dp, dt ds at constant p. And the chain rule applies. And this is actually the same as the chain rule you probably learned in calculus. As long as I'm consistent about what I'm holding constant, this, again, just an example, dv dt at constant s can be written as dv dp at constant s times dp dt at constant s. Since I'm holding s consistently constant, then it's as if I can cross out the p and get dv dt at constant s. Now this one is going to seem counterintuitive. This is the triple product. It looks a little bit like a chain rule, but it's not exactly the same because we're going to change what is being held constant between the different differentials. Okay, it may appear that the dt's cancel, the dv's cancel, the dp's cancel, and that this should equal 1, but notice there's a negative sign. It's actually equal to -1, and the reason, well, I don't know if this is the reason, but notice that I'm holding a different variable constant for each derivative. Now this actually follows from the total derivative. Let me show you. I don't want to do too many derivations here, but this one hopefully will be illustrative. If I express v as a function of t and p, then I can write a total derivative expression. And let's say I set dv equals 0. Then this becomes 0 equals dv dt at constant p times dt plus dv dp at constant t dp. And now I can divide through by dt and move. I'm going to divide through by dt, and I'm going to move this to the other side. So negative dv dt at constant p is going to equal dv dp at constant t times dp dt at constant s. Okay, so if I then divide through by dv dt at constant p, which is going to be, I'm going to copy this. If I flip it, dt dv at constant p, this should equal -1. Remember the negative sign over here. Again, it appears that these derivatives cancel, but I'm actually cycling through what is being held constant, and this should match what I started with, although I shuffled the order. I think I also flipped things. So this is 1 over this is 1 over this, and this is 1 over that. So I could flip each of them and change the order, and they should match. I think I will leave it at that. The next thing is the other mathematical trick here is that a lot of these are state functions. So Gibbs, Helmholtz, enthalpy, entropy, internal energy, those are all state functions. And if a state function is a function of two variables, then the following is true. Again, I'm going to use an example. I'm not writing these things in abstract mathematical terms, but if I pick the Gibbs energy and I say the second derivative with respect to t and then p, it actually doesn't matter the order in which you take, right? So here, d squared g t dp is going to equal d squared g dp dt. And this leads to a very important thing called Maxwell relations, but we're going to get to that. Before we get to Maxwell relations, I'm going to talk about fundamental property relations. So this is where we start marrying the mathematical concepts with the thermodynamic concepts. Okay, let's start with this one. du equals TdS minus PdV. Okay, now you might recognize this as a differential statement of the first law. du is going to equal Q plus W, right? But we're making specific assumption here. Remember that the definition of entropy, ds, is dq reversible over t, so this is dq reversible. And pdv is reversible mechanical work, so we're implying reversibility. And I'm not 100% sure of what I'm about to say, but I believe you have to be working in the reversible regime if you're talking in the differentials, right? In other words, a reversible process involves differential changes in your system. And if I have finite differences, say a finite temperature gradient driving a process, then I don't think it can be described in differential terms. So this can be useful, right? Notice it appears as if u, right, is a function of s and v, and this resembles a total derivative, right? So this du, if I write it as du ds at constant v, ds plus du dv at constant s, dv, it appears that t is du ds at constant v, and minus p is du dv at constant s. So that is true. And I think when you look in these fundamental property relations, you start to see why it's useful to define things like enthalpy. So remember H, I want to list the fundamental property relations together. But so we know that H is equal to U plus PV. And if I say DH is equal to DU plus PdV plus VdP, again, that resembles the chain rule, that's going to equal du is TdS. I'm going to use this fundamental property relation, TdS minus PdV plus PdV plus VdP. These term cancels, and we get dH is TdS plus VdP. Now notice what happens here. It's almost as if by defining H, we're flipping which is the differential and which is the conjugate variable. Right here it's P dV, here it's V dP. And that's actually the point. The natural variables, the variables that most readily define changes in U, turn out to be S and V. And the most natural variables for H are actually S and P. Through similar analysis, I promised I would not try to derive every equation, but you can do similar things by defining A and G. dA is equal to minus S dt minus P dV. dG equals minus S dt plus V dP. And so, again, notice you have TdS, here you have SDT, here you have SDT, and this is unchanged, but for dG, you actually are flipping both the S and T and the V and P, and so G is a powerful function because its natural variables are temperature and pressure, which often are experimentally convenient variables. Now notice that, well, I don't know if you notice, but remember this, right? So if I do second derivatives, right, notice that dg dt at constant p is s. And then if I do a derivative with respect to p, then I get, I will, actually, let me derive this. I want to keep the order the same here. So here, d squared u d v ds is going to be d by dv of du ds at constant v, and that's going to be t. And this also is going to be d squared u ds dv. Du dv is going to be minus p, and dp ds is, d squared u ds dv is going to equal minus dp ds at constant v. And so these two things, actually I should have written constant s here. So these two terms are actually equal to each other, and that's because they come from second derivatives of u, but with the order changed between s and v. So these are known as Maxwell relations. And they're very handy So that's the Maxwell relation that comes from the second derivative of u. So I'm going to write them going down this order. Then come the ones that are related to the dH equation, then the dA, then the dG. And I'm not going to go through it in detail. If you're in my class, you've already had the misfortune of watching me do this in lecture. And okay, so these are handy in thermocalculus. Notice that in many cases, we can take something we can't measure, like ds dp, because we can't directly measure s, and we can express it in terms of things that we can measure or get from an equation of state, like this, for example, you can get from the ideal gas law. I think we're done with the groundwork. Let me just do a quick summary here. So what are the tools at our disposal, right? First of all, with the Gibbs phase rule, we can choose to express each of these variables as functions of any two other variables. The eventual goal is to convert things into things we can calculate or measure. So we have to keep an eye on what we can measure or calculate. Like, for example, we can calculate things from equations of state or material property data. We can estimate derivatives from things like tables of thermodynamic quantities. We can get data on heat capacities. And mathematical tricks include total derivative, flipping of derivatives, chain rule, triple product rule, and the state function concept actually goes into the derivation of Maxwell relations. So I should just list Maxwell relations. And then finally, fundamental property relations. I realize that it is quite challenging when we start solving problems. It's quite challenging to know what mathematical step to take in order to get to the end goal. And I'll try to talk through that as I present problems.